Hi. So my name is Tomer Gabel. This is the third day of the conference, and I'm surprisingly sober. I hope you guys are reasonably sober as well, but if not, that's okay. This is GeeCON. Today we're going to be talking about dependency injection, and I want to start with a bit of full disclosure. When it comes to dependency injection, I was never much of a fan, right? I've been in the software industry and in the Java space specifically for well over 10 years. Spring was already a thing back then. I never got into it. Like, I could never figure out why this is a thing. I did try to do a lot of research for this talk. This is the third time I'm giving this talk, and nothing has changed, so hopefully this still applies. I've done a lot of research around this talk. Basically, this whole talk is my attempt to sort of go back to basics, try to objectively approach the subject, and answer one very simple question. Dependency injection, is that a good thing or not? So to do that, I read a ton of material. I read, a lot of the books, the Martin Fowler stuff, the Uncle Bob books, blog posts, Wikipedia articles, what have you. I talked to a whole bunch of people. I interviewed a few of them. Like, I basically grabbed about 8 random people who are self-professed proponents of DI from within the Israeli software industry, where I'm from. I interviewed them, tried to figure out what their take is. I spent a lot of time thinking about this subject, and eventually what happened is this still turned out to be a rant. So if you're not in a mood to listen to someone complaining about dependency injection for about 45 minutes, you can always leave, but hopefully this will be somewhat entertaining and maybe even educational for you as well. So let's get started. When I say dependency injection, it is very, very likely that, especially as a Java conference, people in the Java space, what you have in mind is something along the lines of this. Yep, seems to be showing up correctly. Right, so this is just a random juice module. This is kind of what people have in mind when dependency injection is a thing that's being discussed. And it doesn't matter if it's juice or it's Spring. Also, it's worth noting that everything I talk about in this presentation doesn't just apply to the Java space, right? You have the same principles, the same technologies in the .NET space. Angular.js as a fundamental design principle is based around dependency injection. So nothing here applies specifically to Java. I'm obviously going to use Java as an example because that's what I'm most comfortable with, and also this is a Java conference. But the same concepts apply to whatever technology you happen to be working in. So when I started off, this is what I had. This is the picture I had in mind when I said dependency injection. That's probably what you're thinking. It was what I was thinking. It turns out that the reality is a little bit more subtle than this, and in order to actually discuss dependency injection in any meaningful way, we first have to figure out what it is, and then unfortunately we're going to find that we actually mean something else, but we'll do a walkthrough, and hopefully everything will make sense in about 5 minutes. So to start with, the D in solid. Is anyone here, raise your hands if you've never heard of the solid principles of OO? Wow, not a single hand, which means you're either completely ignoring me or everyone has heard about it. I'd prefer the latter option. Right, so a lot of people think the D in solid stands for dependency injection. It turns out that that's actually incorrect. So the 5 solid principles of OO were sort of put together or put in that order by Michael Feathers, I think around the year 2000. The D in solid is not actually dependency injection, it's dependency inversion. Now, this talk is not about solid design principles or anything. It's specifically around dependency injection. So we're only going to be focusing on the D. Dependency inversion is not dependency injection. They don't quite mean the same thing, but both of them come into play for the purposes of our discussion here today. Now, dependency inversion is actually a remarkably simple idea that nowadays we kind of take for granted. Right? What it stipulates is that given a dependency, right, we have 2 systems or 2 classes, 2 components in your system. It doesn't really matter what terminology you use. You have 2 things, and one depends on the other. Like in this example, we have our OAuth provider, and presumably it needs some sort of backing user store to actually perform authentication and authorization. Right? So we have our OAuth provider, and it depends on a MySQL user store. Now, what dependency inversion stipulates is that the system A should not directly depend on system B. Instead, it should depend on the abstraction that system B implements. So typically, we would call it an interface. Right? What you do is you extract a general purpose kind of user store interface, you implement it over MySQL, call it MySQL user store, and you depend on that. Now, the reason this is called dependency inversion is that up until the point where the term was coined, which is around 1994 by Uncle Bob, the sort of underlying assumption of how to do software design is just that. Oh, sorry. It's just this. This is how people build software. Now, Uncle Bob postulated that this actually gives you a great deal of decoupling. It means that your implementation of your OAuth provider doesn't care what backing store is actually driving it. Like, it needs to work against the user store as an abstraction. It does not need to know if it's MySQL or Postgres or anything else. And the reason it's called inversion is because if you look at the bottom arrow, the actual implementation of this interface also depends on the abstraction. So it's kind of the reverse order or reverse direction of the dependency compared to what people were used to. This is a very, very, very basic concept. I imagine everyone in this room knows it. So is this a good thing? Yes, it is. It's very much old hat. Nowadays, everyone who does software development, especially in the Java space, kind of builds it that way. This is almost 25 years old, right? We already know this. So it turns out that there have been significant advances in the way we build software over the last 20-odd years. Right. Next. Also, before I proceed, 2 points of order. One, if there are any questions, please raise your hands. Hopefully I'll notice you and stop and you can ask your questions. There is no reason to wait. On the other hand, we'll have time for questions at the end, so if I missed you, then you'll still get your chance. Second, everything I'm going to be talking about in terms of code samples is actually available on a GitHub repo. The link will be at the last slide. And if any of you want to follow the slides because you can't see or because you want to scroll back, the link to the slides is on the GeeCON Twitter tag, so you can look at it. Okay, so dependency inversion. Straightforward, simple, good, wonderful. Let's move on. Dependency injection, as opposed to inversion, is a concept where if you assume the solid principles, like you assume dependency inversion as sort of a first-class approach to building software, asks the following question. Given a dependency, right, who owns the dependency? What is the life cycle of the dependency? So especially sort of journeyman developers who don't necessarily have a lot of experience, a lot of good mentorship, would oftentimes just do the obvious thing and have the depending component instantiate the dependency. Okay, so in this case, we have a user service, and it depends on some sort of user store, and we have the new MySQL user store as part of the initialization of the user service. Right? This is fine in a sense. I mean, it works, but it does 2 things. First of all, it couples very strongly the implementation of the user service to the specific implementation of the user store. Despite the fact that you're depending on an interface, you're actually instantiating the concrete type, so that's a form of coupling. And it ties the life cycle of the user store to the life cycle of the user service, whereas these 2 things might be very much independent. Now, dependency injection stipulates that services should not build their own dependencies, but instead they should receive them and treat them as state. So in this case, we have, once again, our user service, and it takes in a reference to some user store as part of its construction, and it just stores that reference as state and uses that to reference the user store. What dependency injection does not do is it does not tell you how to implement this. So everything on the right here, like receiving the user store through the constructor and then making use of it, this is a complete, fully valid, fully legitimate implementation of dependency injection. right? Dependency injection doesn't say anything about containers or frameworks or runtime or compile time or reflection or any of these things. All it does is it says, if you have a dependency, it is not your job to instantiate the dependency. Just take it in as an argument and use that. Let something else manage the lifecycle of the dependency for you. And the reason is decoupling. Once again, this code is slightly better decoupled than this code. Why? Because it doesn't deal with lifecycle and it doesn't deal with concrete implementations. Simple enough. So, what's the verdict? Well, dependency injection is a very good thing as long as you don't complicate it. If you keep it simple, if you keep it at face value, and you don't add unnecessary complexity, it's actually a very, very simple idea, and it's very powerful. It aids in decoupling, right? But it does not stipulate that you need Spring or Juice or a container or some sort of runtime process to deal with these things. It's just a simple pattern. Now, so far, so good. It turns out that when we say dependency injection and the image we have in our mind is like a Juice module, what we actually refer to is not dependency injection. It's something called inversion of control container. And that's where things get hairy. So inversion of control is not exactly a pattern. It's more of a paradigm. It's more of an approach to designing systems. Now, what inversion of control says is, traditionally, if you were developing software, a piece of software, your software has some sort of entry point, right? At some point, the operating system presumably hands off control to the process where your program is running, and you have your entry point, and from that point on, the control of the system is yours. You get to decide what happens. So you bootstrap your app. If you used to do like 132, for instance, software development 20 years ago, you would have spun up an event loop, started doing dispatch. Whatever it is you needed to do, it was on you. Now, inversion of control typically stipulates that you have some form of third-party framework or container or some sort of underlying middleware that you don't directly get control from and then act on. Instead, what you do is you register your components for whatever job they have to do. You hand them off to the container, and the container maintains control. The container calls into your components instead of you surrendering control back to the operating system. I hope this makes sense, but if not, then the reason is probably the fact that this is a very abstract idea. You'll notice that inversion of control doesn't have anything to do with dependency injection in of itself. By this definition, there's a whole lot of things that could be considered inversion of control containers. So it could be servlet containers, right? If you're building a servlet-based web app, right, you're using Jetty or Tomcat or Glassfish or whatnot, you take your application, you create a descriptor that tells the container, on which URL patterns to call in to which component, to which servlet. You give it all the information it needs to keep doing its job and only call into your app when the time is right, when something meaningful happens. You package it into a WAR file, and then you deploy it on your container. Servlet containers are inversion of control containers. By that same definition, plugin systems are like that. Stream computing, like Spark, right? Spark manages the execution, and it calls into your own, or Storm, if you will, calls into your bolts. Spark calls into your code paths, whatever. Like the fundamental execution model of an inversion of control container is that you register the things that need to happen, and it's the system that takes care of actually executing everything and only calling into your code when necessary. Dependency injection containers is also a form of inversion of control, and that's what we're going to be focusing on today. So when I started off by saying dependency injection is not a Juice module, Juice is an inversion of control container that performs dependency injection for you. I hope the semantics are more or less clear. For the most part, the issues I have are not with dependency injection, they're actually with inversion of control used for dependency injection. In other words, Spring, Juice, and the like. So, If we put those two things together, right, we want dependency injection and we hand off the responsibility for doing dependency injection to some form of container. What does that container do? So fundamentally, Spring or Juice are runtime containers. You register components onto them by some form or other, and they manage the components for you, including their life cycle, including their wiring together. Right? It deals with the life cycle of instantiating your components, of killing off your components, of handing off your components to be wired into depending services or depending other components. That's all it does. Now, why would you use that? Like, this is one of the things that I have a very hard time with is whenever I have this debate with people and ask them, well, why would you use this? Like, you're using Spring. Can you tell me why? Oftentimes, the response is not, it solves this set of problems for me. Oftentimes, the answer is either because it was already like that when I came into the company, which is one possibility. The other possibility is because, well, that's the way I was taught, or that's the way software development is being done today. Right? Spring is so pervasive, and Juice is so pervasive, that you'll be hard-pressed to come into any software project that doesn't use one or the other. And when you try to dig into it and you try to figure out why is it that people use these techniques, use these tools, use these libraries, typically you would find one of these four answers. It helps simplify wiring within your app. Like if you have a big app, a lot of components, a lot of beans, a lot of modules, what have you, then ostensibly it helps you wire these things together much more simply. It simplifies testing. That is the second most common use case for these containers. It allows dynamic configuration. And by configuration here, I'm not referring to your JDBC URLs. I'm referring to the actual configuration of your app, how your app is put together. So a lot of the times, especially with large-scale sort of on-prem enterprise software, you might have different configurations of the actual running components within the system. Not just flags. I'm talking about like wholesale bits of the application that are, shall we say, dynamically decided on depending on the installation. And it helps support AOP. And we're going to be talking about each of these in turn, except we're not actually going to be talking about half of these, because dynamic configuration is essentially bogus. No one does that. What is the last time you've ever come across someone actually SSHing into a server and editing a Spring XML file to reconfigure an app? And by reconfigure, I don't mean adjusting a configuration parameter. I'm talking about adding or removing beans in order to actually make the application behave differently in production anywhere, right? Maybe there are some esoteric use cases for this still, but basically this goes against the grain of everything we've learned about software delivery as an industry over the last 20 years. We're going with packaging, we're going with Docker, immutable deployments, treating your servers like cattle. All of these things sort of mean you don't do this, right? This is manual work. No one ever does this. It just makes no sense. So I'm not even going to spend any more time talking about it. AOP, I could spend all day talking about, and in order to do that, I'd need to probably take some very, very strong medication so I don't blow up. AOP, very clearly for me, is a terrible idea. Now, this is a whole argument in of itself. If you think AOP is a good thing, we should have that argument, but later. For now, let's assume AOP is not really a desirable use case. So I'm not going to spend any time on that. We're going to be focusing on wiring and testing because these are the two major themes that keep popping up whenever I ask the question, why DI? Why Spring? Why Juice? So, to start off, wiring. Everybody loves auto wiring, except the people that don't. There seems to be a strange correlation between people who wake up in the middle of the night and people who hate automatic wiring. I don't know why that is, but let's dig into it a little bit. So this is a sample app. This is a slightly simplified example from a fully public repository actually implementing a full-blown service that approximates something I built at the previous company I was working for, which is Wix. This is actually all you need for a small microservice. You have your database connection, you have some sort of event store because this is an event store system that depends on the database. You have a snapshot store, once again, because this is event sourced, also depending on the database. You have some form of clock and a site service, and all of these things compose basically a component graph, right? These things are built into a directed acyclic graph of dependencies within that composes your application. This is the crux of what your system does. And this is all of the code that initializes these components and wires them together. Now, if we were to implement this as sort of a juice module, here's what it would look like. Right? We have a module, we have our configure entry point, we bind a bunch of interface classes to a bunch of either providers or instances or even just the classes, and we let Juice auto-wire everything for us. Now, it turns out that don't sweat the details, right? The details don't matter. This is just a simple example, but what's important is that the code on the left and the code on the right are intended to do the exact same thing. And it turns out that they're virtually the same code, right? If you look at these, it's about the same volume of code, it's about the same level of complexity of code, and the code basically has the same responsibility. So, what a lot of people would tell you is that having a dependency injection container, an IOC container for dependency injection, really helps wire things together, and it really simplifies wiring, and it saves a lot of boilerplate, and blah, blah, blah. I call bullshit on that, because, first of all, it turns out wiring code, first of all, isn't a lot of code. Right? Even if you treat it as boilerplate, and I'll circle back to challenge that statement in a second, it's not that much boilerplate, right? It doesn't really save you that much code. Writing wiring code is very, very trivial. More importantly, though, there are a lot of downsides to not wiring your components manually. First of all, sorry about that. First of all, there's the trivial thing that, especially with modern-day DI containers that do like class path scanning, especially Spring, it negatively affects your startup time. But never mind that. That's not a real problem. The problem is with code navigability. Right? Whenever your application starts up and it bootstraps all of the components that make it up, right? Whether it's database connections and DAO objects, DAO being data access objects, and your persistence layers and your business logic and all of these things put together, this is the core of your app. This is the very definition of what your app does. It is the sole responsibility of your application, right? If it's not wired together, by definition, it's not part of your app. So treating that as boilerplate is actually remarkably dangerous, because if these components comprise what your app does, they're not boilerplate. They're fundamental to your app. Now, imagine that once you wrote the auto-wiring code, 6 or 12 months later, someone else comes in and they're trying to figure out, you know, I know what the interfaces are. I kind of know what the concrete implementations could be. I want to know what actually goes on. I want to figure out what the system does. I want to figure out what the bootstrapping process is. I want to know if something gets initialized before something else. I want to know what the concrete implementations, and if you use AOP, I want to know what decorators I use. Right? If all of these things are automatically done by some form of container, it becomes really, really hard to reason about. Whereas if it's straightforward wiring code, you just go to definition, you find the entry point for the app, you have everything right in front of your eyes. You can't mess it up. You can't not have something that's part of your app show up right in front of your face. Whereas typically with any project that uses IOC, any form of IOC really, then it becomes really, really hard to figure out just what is going on. Right? I have a servlet. That servlet is managed by a bunch of filters, and it needs a bunch of dependencies. What actual implementation drives that servlet? Right? That seems to be a question you should be able to answer with a simple code lookup. But because of the automatic wiring, because of the implicit nature of what Juice or Spring do for you, it actually becomes very, very hard sometimes to figure out what is going on, what are the components at play. So code navigability actually suffers a lot, and because of the sort of reflective runtime nature of the way most of these frameworks do their job, it turns out that you actually have a lot of tangible downsides. So for instance, imagine that you did not register a particular bean or did not bind a particular interface, right? Because you forgot. You're going to find it out in runtime. Now, you might argue that tests are a valid way to sort of catch all of these things ahead of time. It's not a real problem. I would argue that the compiler is much, much more suited to figuring out that you forgot to feed an argument into a class, right? Oh, sorry. I missed that. So also, there are a lot of other sort of gnarly bits. Like, for instance, imagine you have two database connections, and you have two components that rely on those database connections, and they're completely separate, completely in isolation. In order to instruct your dependency injection container to actually choose the right connection for the right use case, you typically have to either annotate it with like qualifier in Spring, or you have to do all sorts of hacky, ugly things as part of your module to make sure that your database connection only applies to a particular module in Juice. Like, you have to do all of these things instead of just passing the right argument. Just instantiate two things, pass them as is. Like, it's a very, very complex solution to a non-problem. And not only does it not really help, it actually hampers, because it becomes that much harder to reason about the structure of your app. The other argument is that it helps simplify testing. Now, proponents of inversion and control and dependency injection will tell you that it's invaluable for testing, because if you want to test a new part of your app, here's what you do. You spin up a container, you swap out components that you're not interested in with mocks, because mocks are good, I guess, and you're done, ostensibly. Now, before we move on to why this is a terrible idea, I wanna show you an interesting definition of a word, like a dictionary definition of the word deconstruction. It is a literary technique that regards meaning as resulting from the differences between words rather than the things they actually mean. So basically, if you're doing this, if you're spinning up your whole application and then you're chopping out parts of it and replacing it with mocks, your tests start focusing on the setup. They start focusing on what are the things I need to swap out, instead of focusing on what are the things I need to test. Which brings us to the term deconstructive testing. Let's clarify that. Imagine that I want to test my MySQL event store, right? Just that. I want to write a unit or integration or acceptance test for my MySQL event store. Well, what does it need? Basically, it's some form of data access layer object, so it probably needs some data source or some form of database connection. And that's all it needs, right? If you want to test that your database connectivity, your database access code, your SQL and update and DML statements work, typically all you need is your business logic and a database, right? On the other hand, if you do it with Spring or Juice or some form of dependency injection, you start with your entire system, your entire object graph that comprises the rest of your system, and then you start mocking stuff out. So for instance, we might have the MySQL snapshot store, which is a separate data access object with a separate data source. And we might have some source for clock, so that we can actually apply timestamps and stuff. So we mock these out. Right, and the top level object is like the service that actually does something useful with this. We mock that out because we don't care. It's not part of our test. This is an insane way to do testing. This makes it very, very hard to get your test harnesses right. It introduces a lot of accidental complexity to your test setup. Like, why would a test that deals with the things on the left even have to know about everything that happens on the right side of the screen, right? Why would you take a full-blown object graph and replace parts of it when you only want to test a very, very, very small subset of that graph. Right? It just makes everything so much harder. And then not only is this hard to reason about, because suddenly your small system that you're testing has actually a lot of cruft around that you need to deal with as part of your setup, you also have to deal with a lot of subtle interactions within your system. Like, for instance, especially if you have like AOP type things, or you have some interceptors or proxies or all these nice modern day techniques for making your development faster. It turns out that actually this is the root cause of a lot of interaction between components that should not interact. Right? For instance, what's this clock doing here? Does it actually affect? Maybe if I mock it with a system clock, mock the system clock with like a test clock, does it affect the system clock? Does it get read by other components? Maybe some other component as part of its initialization process assumes certain things about the graph. There are a lot of small things that can happen because you didn't think about them, because suddenly the world you're dealing with as software engineers within your particular test actually has a lot of these small interfaces to the outer world that you might not even realize. You might have bytecode weaving that does things with your code that you didn't even realize, right? More crucially, though, this means that your tests do not reflect your unit structure. Like, take a look at this again, right? Your unit structure is a data access object and a data source. That's your unit. That is the world you need to concern yourself with when writing and testing the code on Lyft. If there's anything else, then your test does no longer accurately reflects the structure of the components and the wiring in your system. If your test setup for your MySQL event store needs to concern itself with mocking other stuff that is not part of that object graph, now the next person reading your test 6 or 12 months in is going to look at your setup code and go like, wait, why is this being mocked out? How does this even relate to the system I'm currently tasked with fixing a bug on, or rewriting, or migrating to Postgres? Right? That just makes everything that much harder to get. And that leads to poor design. One of the more common themes that I've found in large code bases that are based on Spring and Juice is the proliferation of dependencies. If you write your object graphs manually, if you strictly only require the things you care about, and it's hard to add things to that list unintentionally, then your code reflects exactly the functions that the function that it's supposed to fulfill. On the other hand, if you have this cloud of stuff that you can always just reach out to and ask, right? Just by adding a constructor parameter, suddenly you can have access to virtually everything you want, because no one is tasked with actually writing the code that instantiates your component and has to pass in that argument. It becomes really, 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 really easy to demand things of your system that you don't really need. Right? Imagine that you just need, I don't know, some form of utility function to deal with whatever, do path canonization. Right? Suddenly, instead of either writing a small unit and testing it, and sure, you might have a bit of duplicate code, but everything is very nicely encapsulated, you just reach out to some utility object. Right? It becomes very easy because no one has to feed that utility object and then pass along from object to object to object in your object graph. On the other hand, it just means you added a dependency on something that you don't really need, or that you might need a small subset of, but because it's so easy, you might have accidentally actually added a dependency in a whole stack of things. So the end result is that with a substantial enough system, if you actually want to do some refactoring, typically you don't really know where the dependencies are. You don't actually know whether deleting a utility class is going to screw up some test in a completely random other part of the system because someone added it as a dependency because nothing stopped them. Nothing caused them to pause and say, wait a minute, is this actually a dependency? Do I actually need this thing? There is a cost associated to putting two pieces of code together, especially if the people who wrote them are not the same person or not in the same building or not even in the same company. Dependency injection containers make it that much easier to do that, and they make the cost not go away. The cost is still there. You're just going to have to pay it with interest 12 months in because you don't have that extra step of, wait, this is too complex. I don't even need this. Right? It doesn't give you that opportunity to revisit your code and say, does this code have the most minimal surface area that it possibly can? And that is a genuine problem. So, to summarize, inversion of control for DI doesn't really solve anything. It's a solution in search of a problem. The corollary of that is that with huge code bases, okay, one of the common themes in the discussions I had is, well, how do you build a system this large without having an IOC container to help you out? So with huge code bases, other favorite names mean like monoliths, enterprise, corporate software, whatever. Legacy Java code bases from 15 years ago. With really, really, really big code bases, IOC enables a trade-off. Okay, the bigger systems are, right, generally, and this is true for any software system, it has nothing to do with IOC. The bigger the code base is, the more complex, the more interactions, the more components you have, the more developer discipline you need to actually keep a coherent image of the system in your head. And it becomes exponentially harder the bigger the system becomes, right? So IOC gives you this trade-off. Like if you're willing to forgo that developer discipline, you want to hire, shall we say, less disciplined or less experienced developers who don't have the discipline, and you want them to be productive from day one, just come in, start writing code. IOC enables that, but in return, you give up a lot of coherence and a lot of just simplicity and sense in your code. There's a reason why, well, two arguments. Argument number one, there is a reason why systems that are big are really, really, really hard to get into. Okay, for any system, I imagine a lot of the people in this room have had this experience of joining a new company, having this legacy monolithic system that no one really knows very well, but you sort of have to maintain every now and again because it's business critical. And once you go into the code base, you just lose yourself because there's so much stuff going on, and it's impossible to know, like, for a given use case, which bit of code you need to work on. And it's really hard to navigate from one point of responsibility of the system to another. The reason is size. It becomes increasingly harder to maintain any form of coherence in a code base the bigger it gets, without having extremely disciplined developers. And IOC makes the problem not go away, but it makes it seemingly a non-issue at first, and you pay the cost only later. The second argument is that if you look at the way the industry is going over the last 20 years, we've actually internalized this lesson very, very well. And the name we gave one of the solutions, the name we gave it is microservices, right? The whole argument around microservices is kind of stupid. It's like, how small should a microservice be? Should it be 100 lines of code, 1,000, 3,000? Should it be a 2-pizza team? Should it be something that you can keep in your head? All of those arguments are meaningless because the fact that we're having that argument means we have already internalized the important lesson, which is big systems are extremely hard to deal with, are extremely hard to maintain. They require a lot of developer discipline, right? So we're building our systems smaller. We're trying to cut down our business into bounded contexts and encapsulate them in these relatively small units that we call microservices. And the reason is so that we don't have to hire exceedingly disciplined developers to keep the whole system, that are capable of keeping the whole system in their head and maintaining the system in a coherent way. IOC gives you the illusion that you can have both the size and the coherency. But in fact, you always give one of the two up. And large systems based on these containers are not coherent and are very, very hard to get into and maintain. So, the corollary. if you're realizing the benefit of having an IOC container, you're already up shit creek without a paddle. If you're working on a software system that's incredibly large and you can't imagine giving Spring or Juice or whatever up because it makes everything just, you have to wire things and you don't know where things are, you're already in deep shit. Right? And a lot of us are in that position, and there's not much we can do about it, except learn the lesson and engineer our next system significantly better, smaller, and without solutions that don't actually solve any problems. And with that, I am done. All of the code examples, including a full-fledged implementation of a service with and without Juice, are on that link up there on GitHub. And with that, if there are any questions, I'd be very happy to take them. Thank you very much.